All right, we'll be looking at page 468, problem 8.38. It's dealing with the geometric distribution. The problem says we're going to conduct an experiment where we roll a single die until we get a prime number. It says let x be the number of rolls required to get the first prime. All right, so we have discussed geometric distribution. It has four characteristics. 1, 2 outcomes, success or failure. 2, the trials are independent. 3, the probability of success is constant. And 4, we're going to try until we succeed. This fourth characteristic is where the geometric differs from the binomial. The first three, same as the binomial. Fourth, try until succeed, whereas in the binomial, the number of trials are fixed. All right. So in this problem, we're going to verify first. Verify that this is geometric. Verify geometric setting. Well, it says we're going to roll a die, and we want a prime, so it can be prime or not prime. 2 outcomes in this case, prime or not prime. We sometimes call that little character prime. It's like prime. We can have a prime or we can have not a prime. Are the trials independent? Certainly by now you know that rolling a die independent. Rolling die is independent. That is, the die has no memory. Rolling a 3 on this roll will give us no predictive value for the next roll. If we happen to roll 5 3s in a row, well, the chance that this next one's going to be a 3 will be 1 in 6. Probability of success is constant. Half of the rolls will be prime and half not. So in this case, the probability of success rolling a prime will stay as 1/2. Try until we succeed. That's what the problem says. We're going to roll until we get a prime. So indeed, we fit here. So we have all 4 of our characteristics. Verify the geometric setting. Done. All right. B says construct a probability distribution table to include 5 entries. All right. B. They define x to be number of rolls until first prime. Number of rolls until first prime. That is our geometric random variable. Okay, so we construct our table. X and probability of x. All right. Well, the chance of us on the first roll getting a prime is 1/2. And that should be clear. Now, we want to look at the chance that the second roll is my first prime. Well, I'm going to write that out right here. We want the probability that x is equal to 2. What we're saying is that's going to be a fail then success. We don't get it on the first roll, we do get it on the second roll. Well, the chance of a fail then success is, the chance of a fail is 1/2 because 50% of the time we will get a prime, 50% we won't. The chance of success is 1/2, so this is 1/2 times 1/2, which is 1/4. Okay, so the chance that the first success comes on the second roll is 1/4. Now we're looking at 3, 4, and 5. Well, the chance that the first success is on the third roll, probability that x is 3, well, that's going to be fail, success. 2 fails and then a success. In this case, that's 2 1/2s, but then another 1/2. It's still, even though the reason we have strictly 1/2s here is because the complement of 1/2 is 1/2. All right, so in this case, it's 1/2 times 1/2 times 1/2. Well, that's 1/8. And I hope that you can see the pattern that's developing. This is be 1/2, this is 1/4, this is 1/8. The next one will be 1/16. That is 3 fails and then a success. It's still 1/2 to the 4th power. And then the first one being on the 5th is 1/32. So this is my PDF for the first 5 rolls. No matter what the probability of success is, the most likely single roll for success is the first roll. And if you think about it, that makes sense. Let's assume that the probability of success was 0.9. The chance that we would succeed on the first roll would be 0.9. The chance the first success would be in the second roll would be 0.1, that is, we fail here, and then 0.9, we succeed here. So all of these successive rolls will be products of numbers less than 1. Therefore, it's always going to be decreasing. No matter what your likelihood of success is, your most likely first success is the very first roll. Will it be likely that it's the first roll? Well, that'll depend on what the probability of success is, but it is the most likely single success. All right. C. Construct a graph of the PDF. Okay. So x-axis, the y-axis is going to be my probability, and the x-axis is number of rolls. And we're going to look at 1, 2, 3, 4, 5. All right. Counting in this direction, let's go by 0.2. 0.2, 0.4, 0.6. In our first roll, we had 1/2. Chance at the first roll, 1/2. Second roll, 1/4. And what we'll see here is each successive bar is going to be precisely 1/2 because that is our complement, our probability of a failure. 1/8, that's 0.125. 1/2 of the previous bar. 1/16, 1/2 of that bar. 1/32, roughly 3%. So you see it's a steadily decreasing, each bar being 1/2 of the previous one. Okay. D, construct the CDF of X and plot its histogram. D. CDF, cumulative distribution function. All right. X and C of X. Well, we're talking about the outcomes and the sum of all of the probabilities less than. Well, the first one is still the same, 1/2, because there is nothing below the 1. Now 2. What we're saying here is, what is the sum of the probabilities for 2 and 1? Well, 2 was 1/4, 1 was 1/2. 1/4 plus 1/2 is 3/4. 3. Now we need 3, 2, and 1. That is 1/2 plus 1/4 plus 1/8. Well, 1/2 is 4/8, 1/4 is 2/8, and 1/8 is 7/8. And you can probably already see what's happening here. 1/2, 3/4, 7/8. The fourth one is 7/8, the sum of all these, then plus 1/16. Well, 7/8 is 14/16, and 1/16 is 15/16. what you're going to see here, we're going to do this for the rest of our lives, and this number won't reach 1, but it will be closer and closer to 1. It will tend to 1. For those of y'all in calculus, we talk about the limit. This will approach 1 as we go to infinity. The fifth one will be 15/16 for the first 4, plus 1 over 32. That will be 31 over 32. All right. I'm not going to construct the histogram. What you would see is it would be similar to this, but in the opposite direction. It would start at 1/2 and increase. It'll approach 1. Each successive bar would be slightly, incrementally smaller than the previous one. All right. We won't construct that histogram, but you have the idea. Lastly, E. E. Use the formula for sum of a geometric sequence to show the probability in the PDF table of x add to 1. What they're saying is we want to show that this will sum to 1 as we go to infinity. Even though it never actually, we could conceivably roll for forever and never roll a prime. The sum of this series will indeed sum to 1. From page 446, pardon me, page 466, sum of a geometric series those of you in pre-calculus and in calculus may be familiar with this. This sum is equal to A divided by 1 minus R, where A is the first term and R is the rate, that is our multiplier. For our purposes here, R is the complement. It's the probability of failure. And you can refer back to page 466 and they will show how we arrive at that. Alright, so for our problem, A, our first term, well, our first term, 1 went to 1/2. So A in this case is a 1/2. A is 1/2. Divide by 1 minus R, that's the probability of failure. That's 1 minus a 1/2. Well, clearly that's 1/2. So this is 1/2 divided by 1/2. Well, that is indeed 1. So the sum of our series will be 1. And you will see that in fact it'll always be 1 because A, this first term, will always be the probability of success. Our first term will be the probability of success. Well, R, the probability of failure, is the complement. So if we do 1 minus the complement, well, that is indeed also the probability of success. So essentially this is probability of success divided probability of success. It will always be 1. Alright, with that information, you should be able to try 8.39 now.